Hello, dear students. In this video, we continue the concept of nonlinear programming by explaining and reviewing some types of nonlinear programming problems and then review the next part of these types, that is the unconstrained nonlinear programming problems with one variable unconstrained optimization, and review the bisection method that we apply in this part. Let's continue. In an unconstrained optimization, the necessary condition that a particular solution x equal to x star be optimal when fx is a differentiable function. What is the meaning of that? Easily, it could be derived. Okay, it's derivable. That means the derivation of f based on xj equal to 0 at x equal to x star for j for 1, 2 to n. So one important item, when fx is a concave function, this condition also is sufficient. So then solving for x star reduces to solving the system of n equations obtained by setting the n partial derivative equal to 0. In this part here, we just want to review the different types of nonlinear programming problems, okay? And in the next part, we clarify each of these items. So let's go to the next slide. From now on, we just review some types of nonlinear programming as the types, and we don't enter in future in the solution of these types of nonlinear programming. But guys, these parts will help you in the weekly test and the part of test in our exam. So the next types of nonlinear programming problem is linearly constrained optimization that are characterized by constraints that completely fit linear programming. Okay, so in these types, all the constraint functions are linear. Okay, so that all the GIX constraint function are linear. As you remember, in the very first part of this chapter, we just separated our constraint with GIX. So, but the objective function fx is nonlinear. Okay, when we are talking about nonlinear, nonlinear could be whatever type of the example. Okay, x elevated to 11, elevated to 5, elevated to 8, whatever. Okay, so the problem is considerably simplified by having just one nonlinear function to take into account, along with a linear programming feasible region. Obviously, as you remember in graphical solution, when we had all the constraints as linear and objective function nonlinear, the curves that enter to the feasible region is exactly the same type of example. A number of special algorithms based upon expanding the simplex method to consider the nonlinear objective function have been developed. Okay. The other type of nonlinear programming is a type that we name it as quadratic programming. Quadratic programming has a similarity with linearly constrained optimization, that as you see here, it has linear constraints, but with one difference. What difference is a special form of linearly constrained optimization that objective function should be quadratic and concave. We know what is concave, but quadratic means one part should has an elevation equal to 2. For example, x1 elevated to 2, or x1 multiplied by x3, 1 plus 1, it's 2. Okay, so it is the meaning of quadratic programming. That quadratic programming problems again have linear constraint, but now the objective function fx being maximized must be both quadratic and concave. Thus, in addition to the concave assumption, the only difference between such a problem and the linear programming problem is that some of the terms in the objective function involve the square of a variable of the product of two variables. Okay, so this square is important. For those who are interested, you can review this part in future in section 13.7, but it's not the part of our class. So here is just a written explanation of the previous slide that I gave you about linearly constrained optimization. If you want, you can review those voices with these written parts. The next two similar types of nonlinear programming problems are convex programming and separable programming problems that in the next two slides I review the explanation of them, and we see what is the small difference between these two types of programming problems. So, convex programming covers a broad class of problems that actually encompasses as special cases all the preceding types when fx is a concave function to be maximized. Okay, so continuing to assume the general problem form presented at the beginning of the chapter, the assumptions are that fx is a concave function, each jix is a convex function. So, as you see, to just review what we learned as a general form of the nonlinear programming, okay? If the objective function is concave and all the constraints functions are convex, this problem is a convex programming problem in a general form. Let's review our separable programming. Separable programming is a special case of convex programming where the one additional assumption is that all the fx and gix functions are separable functions. As you remember, for example, I give you an example. If I have one objective function f x1 and x2 equal to 126x1 minus 9x1 squared plus 182x2 minus 13x2 squared, I can separate this one, okay, as fx1 and x2 to fx1 plus fx2, f1x1 plus f2x2. So my f1 x1 is 126x1 minus 9x1 squared, and my f2 x2 is 182x2 minus 13x2 squared. Okay, so a separable function is a function where each term involves just a single variable. Okay, so single variable, it means that has a term as, for example, 4x1, x2, x3 is not possible, or 4x1, x2 is not possible. Single variable, so that the function is separable into a sum of function of individual variables. For example, if fx is a separable function, It can be expressed as fx, the summation of fj xj, when j is from 1 to n, is exactly the example that I gave you minutes ago. The next type of nonlinear programming problem is a non-convex programming that encompasses all nonlinear programming problems that do not satisfy the assumption of convex programming. Now, even if you are successful in finding a local maximum, there is no assurance that it also will be a global maximum. Therefore, there is no algorithm that will find an optimal solution for all such problems. However, there do exist some algorithms that are relatively well suited for exploring various parts of the feasible region and perhaps finding a global maximum in the process. When we apply nonlinear programming to engineering design problems, as well as certain economic and statistic problems, the objective function and the constraint function frequently take the form something like this, okay? Where it's summation of Ci multiplied by Pix. And Pix is x1 elevated by ai1, x2 elevated by ai2, up to xn elevated by an ai. And in such cases, the Ci and aij typically represent physical constants, and obviously the xi, okay, or xj are designed variables. These functions generally are neither convex or concave, so the technique of convex programming cannot be applied directly to these types of problems that we name them as geometric programming. Let's review in our next slide what can we do, for this type of examples. To continue the previous slide, okay, when we were talking about Ci, aij, and xj, that these functions generally are neither convex or concave, we should review one technique, okay? There is one important case where the problem can be transformed to an equivalent convex programming problem, okay? In this case, where all Ci coefficients in each functions are strictly positive, okay? This one is very important, so that the functions are generalized positive polynomials, now called posinomials, okay, positive, and the objective function is to be minimized, okay? So, to this end, the equivalent convex programming problem with decision variables y1, y2, and yn is obtained by settings, okay? So what do we do to change this one to a category of convex programming? We need to just change the variables, the decision variables, xj to one new variable. To this end, we need to only substitute our xj to e elevated to yj, and the problem will be converted to a convex programming and should be solved with the other solutions that we learned before. The other type of nonlinear programming problem is a fractional programming, okay? That the objective function takes the form of a ratio of two functions, The approach is try to transform problem to standard type. In our next slides, we review briefly this type of nonlinear programming in its explanation. Suppose that the objective function is in the form of fraction, something like this, maximization fx, that is sorry, the fraction of f1x to f2x. Such fractional programming problems arise, for example, when one is maximize the ratio of output, for example, the F1 to person hour, or profit to capital expended, or expected value to standard deviation of some measure of performance for an investment portfolio. So, for example, return to risk. Some special solution procedures have been developed for certain forms of F1x and F2x. In our next slides, we review one of them. Pay attention that one of the most efficient solutions in the majority of nonlinear programming problems is using the equivalent function, okay? As you see here, when it can be done, the most straightforward approach to solving a fraction programming, okay, is to transform it to an equivalent problem of a standard type of which effective solution procedures already are available. To illustrate, suppose the fx is of the linear fraction programming problem, okay, that is cx plus c0 divided by dx plus d0, where c and d obviously are row vectors, x is a column vector, and c0 and d0 are scalars, okay, for these two functions. What we just suppose that f1x and f2x that we had in previous slide are two linear fractional programming with this form. Okay. Also, we can assume that our constraints gix are linear, so that the constraints in matrix form are ax less than or equal to b, and the variables are non-negative. Okay, it's a typical form of linear programming when the constraints are linear in the form of a matrix A multiplied by x's less than or equal to right hand side, that is b, and the constraint for the variables is that they are non-negative. So, to make this problem solvable, we need to assume these two equivalents, a new variable y as x divided by dx plus d0 and t1 divided by dx plus d0. Okay, so as we can see, we can write this objective function that we had in the previous slide, okay, cx plus c0 divided by dx plus d0, okay? We can write this one as cx divided by dx plus d0 plus c0 divided by dx plus d0. Okay, so based on this definition that I have here and here, I can say that this one is my y, cy, okay, c multiplied by y plus c0, this c0 multiplied by t. As you see here, easily I have an objective function that is linear, okay, maximizing z, it's cy plus c0t, and obviously when we had ax less than or equal to b in a typical form of our linear programming, I can write this type of constraints based on this constraint for my problem. And obviously, my new variables that are y and t should be greater than or equal to 0, non-negative. So what did we do? A fractional programming problem based on these equivalent functions. We converted it to a linear programming. Okay? And the last type of nonlinear programming problem is the complementarity problem that wants to find a feasible solution for the set of constraints w equal to fz when w and z both of them are negative, that also satisfies the complementarity constraint, that is w elevated to t multiplied by z is equal to 0. But this part we don't review it, and here we close this topic. The simplest case of nonlinear programming is unconstrained optimization when we have only a single variable. Okay, that means the n equal to 1. We only have one x as a variable, where the differentiable function fx to be maximized is convex. Okay, so with concave differential function, it's very important, it should be concave. Okay, the necessary and sufficient condition for a particular solution x equal to x star to be optimal is the first derivation of that function based on x is equal to 0. So x star, that is our optimality, is obtained. So for this type of nonlinear programming, in this section we learn two different methods. In our next slide, we see one of them to understand it better. In this slide, we have written all the explanations that I gave you in the previous slide, okay? That the necessary and sufficient condition for a particular solution x equal to x star to be optimal, a global maximum, okay? As you remember, the concept of local and global is that the first derivation is equal to 0. For one variable unconstrained optimization, in this part, we review two methods, the bisection method and Newton's method. The approach is to find a sequence of trial solutions that leads toward an optimal solution. Okay, so we find the possible interval of the solutions, and then step by step in different iterations we try to make smaller this interval and find the optimal solutions. Now let's review the bisection method. For those who are interested to read more of this, you can find this explanation in the page 564 of the book Hillier and Lieberman. Now we review the bisection method, and to clarify better this concept, we finish this video with one thorough example of this part. This search procedure always can be applied when fx is concave, obviously, as we reviewed before, but also it can be hold when the second derivative is positive as well, okay, for some values, but none of them, but sorry, not all of them. It also can be used for certain other functions as well, as I told you. In particular, if x star denotes the optimal solution, all the possibilities that happen are these three forms. That if the first derivation of fx is greater than 0 if x is less than x star. If x is greater than x star, the first derivation of fx is less than 0, and in the case of x equal to x star, this derivation is equal to 0. In our next slides, in our example, we clarify this topic. To apply the bisection method, we need to define some points, some information that are important for our example. What are them? X prime is the current trial solution that we learn how to calculate it. X bar down, okay, this one is the current lower bound on X star. X bar up is current upper bound on X star. Obviously, our X prime should be somewhere between these two, lower bound and upper bound, and the error of tolerance for X star. Because as you see, all these solutions and all these methods that we learn are trial methods, okay? That the example defines an error, this epsilon, okay, that says up to what level we accept our X star as a optimal solution, okay? As we learned, there is a stop rule, okay, that helps us to understand when this solution is optimal. So, although there are several reasonable rules for selecting each new trial solution, the one used is the bisection method is the midpoint rule, traditionally called the Bolzano search plan as well, which says simply to select the midpoint between the two current bounds that we learn in the next slide. Okay, easily to solve and to find the midpoint, okay, we should find an average between these two bounds. So to initialize this problem, as we discussed in the previous slide, we need to select an epsilon, okay, that normally the example gives this epsilon to us, and find an initial x bar down and x bar, okay, by inspection or by respectively finding any value of x at which the derivation is positive and then negative. Select an initial trial solution. As I told you in the previous slide, the initial solution would be something equal to the average of upper bound and lower bound that gives us this x prime as our solution. In the next slides, we'll review the iterations that we should pass to find the optimal solution based on bisection method. So as you see here in this slide, these are the very simple steps and iterations for our bisection method. What are them? After finding our x prime as the formula of the previous slide, we need to evaluate, okay, evaluate our fx by the derivation of it. As you remember, there were three possibilities, okay, for our result: greater than 0, less than 0, or equal to 0. If this derivation is greater than or equal to 0, we need to reset our bound and put the current x prime as our x bar down, okay? Vice versa, if it's less than or equal to 0, we need to reset and put our upper bound equal to the current x prime. What happens here? Guys, we are making a smaller and smaller our range of the possible data for our problem, okay? When we stop our procedure, we stop our procedure that when the x bar upper bound minus lower bound is less than or equal to 2 epsilon. The epsilon is the one that example gives us. Whatever iteration this one happens, okay, it means that the x prime that we have, the current x prime, is the optimal solution, so that the new x prime must be within the function of x star and we stop. Otherwise, we need to repeat our iterations up to achieving this part. So to clarify this item, let's review one example. Suppose that we have this objective function 12x minus 3x4 minus 2x6, and it asks us to solve it by bisection method. The first step to see if bisection method can be applied safely is to check if our objective function is concave. To this end, as we learned before, easily we need to calculate the first and the second derivation of that objective function. As you see here, the second has this form, minus 12 multiplied by 1 positive parenthesis. But because this one is minus 12, so this one is always negative, less than or equal to 0 for all x's. So because the second derivation is non-positive everywhere, fx is a concave function. So the bisection method can be safely applied to find its global maximum. Okay, so global maximum, why? Because it's concave. Now let's apply and find our upper bound and lower bound to start our solution. As you see here, this is the graphical illustration of this example. Fx equal to 12x minus 3x4 minus 2x6. So when we are talking about maximum global, it should be something here. Now we want to find this objective function for which point it gives us this maximum. And as you see here, from this point to this point gives us this positivity. And outside of this, it's our negative, okay? So we can find in a trial form our upper bound and lower bound, okay? So for example, here, if I put the lower bound equal to 0, okay, and upper bound equal to, I don't know, something between here, 1.25, it's possible. But to make a guarantee and to understand it better, I put the upper bound equal to 2. What happens? In each iteration, it makes the smaller and smaller, okay? And it enters, okay, for example, if the first iteration will be something like this, maybe this next iteration will be something like this, the next one comes to this, okay, the next inside, and little by little finding the optimal solution. Okay, these are the ranges that we are talking about them. Okay, so the first range is important, but not that much. The only option that happens is the iterations may be more than the other forms, okay? But it's totally correct. So to this end, we define our x bar down and x bar as 0 and 2. So obviously, our x prime is 2 plus 0 divided by 2, okay? That is 1. So we start with 1x prime equal to 1. And we know that our epsilon of this example is 0.01. Why? Easy. The example gives us this epsilon. Let's review next slides. So, as you see here, this is the explanation. A quick inspection of this function indicates that fx is positive for small positive values of x, but it is negative for x less than 0 or x greater than 2. Okay, this one that we decided to have our lower bound and our upper bound. So as you remember, in the previous slide, we calculated x prime, okay, and let's epsilon equal to 0.01. And just review the stopping rule is less than, or x bar minus x bar down is less than or equal to 2 epsilon. Epsilon is 0.01. So here is, let me clean this one, is 0.02. It means that whenever the difference of our upper bound and lower bound is less than or equal to 0.02, we stop and we find our optimal solution. In our next slide, table 13.1, we review the different iterations of bisection method, okay, that will help us to find this optimal solution that is 0.836. As you remember, we started with 1 and now we find it as 0.836, and as two intervals and one interval, we started from 0 to 2. As you see here, we make it smaller and smaller, that this x star clearly and obviously fits in this lower bound and our upper bound. Let's review the last slide. So this is the summary of our iterations in this example. The iteration 0, we start with 0 and 2 as our lower bound and our upper bound. That the new x prime is the average of them, that is 1. So if I substitute this 1 in the first derivation of my function, it will give me minus 12. Okay, it will give me minus 12. So as you remember in the iterations of our example, when the first derivation of objective function is less than or equal to 0, we need to substitute this x prime as the next x bar, okay, the upper bound for the next iteration. As you see here, this one comes here. So for sure, our new x prime is 0 plus 1 divided by 2, that is 0.5. And at the same time, we check our stopping rule. What was our stopping rule? X bar minus x bar down less than or equal to 0.02. For example, for iteration 0, as you see here, 2 minus 0 is not less than or equal to 0.02. So we need to follow, and it means that this one is not our optimal solution. Again, I put this 0.5 in my first derivation. That gives me plus 10.12. Okay, so now our objective, our derivation, first derivation is positive. So our method says if this one is positive, now I should substitute my new x prime with my lower bound. So as you see here, this 0.5 comes here, 0.5, and it gives me 0.75. Okay, again, I should continue, put this 0.75 in the first derivation, it gives me positive. Again, I substitute with the lower bound, and here it gives me the new x prime. When I put this one, it gives me negative, and I will have this new x prime. I need to follow these different iterations, but always, guys, I should check my stopping rule in each of our steps. Whenever this one is valid, the optimal solution is obtained. Okay, like what we have here, the optimal solution is obtained here. So means that if I subtract from this one this item, it means that 0.84375 minus 0.828125 should be less than or equal to 0.02. Let's check this one. 84375 minus 828125. It gives me the result 0.015625. That is less than or equal to 0.02. So the stopping rule is valid, and my optimal solution is 0.8359375. So this is the explanation of bisection method.